Set theory describes relationships between events, and probability theory introduces the concept of size to the sample space. These events are the basic building blocks of a risk analysis. One way to describe an event is as something that could happen, projected into the present as certain, and this is no matter how likely or unlikely the event may be. For example, we can say an earthquake could occur in September, or we can project into the present and say an earthquake occurs in September. This is going to be very important when we start building event trees, because in an event tree, the events are conditional to or dependent on the occurrence of the prior events in the tree. We'll cover more on that later. Venn diagrams can be very helpful in understanding how different events are related. The rectangular box shown here represents the sample space S. All possible outcomes are encompassed by the sample space, such that it has a probability of 1. In this example, there are 3 different events that can occur: events A, B, and C. Each of these events has a probability between 0 and 1. Event A might be a concentrated leak erosion failure mode, and event B might be a backward erosion piping failure mode. Breach can occur by either failure mode, or theoretically, breach could occur due to both at the same time, which is why you see some overlap between those circles in the diagram. Event C is mutually exclusive because it cannot occur together with events A or B. Perhaps event C could be a failure due to an earthquake without a flood, which is often assumed to be mutually exclusive. We'll cover mutually exclusive events a little later in this module. The union and intersection of events was briefly introduced on the prior slide. The union of events is calculated by summing the probability of the events minus the probability of their overlap. It is the likelihood that event A or B or both occurs. The total probability of failure that we calculate during a risk assessment is the union of potential failure modes, which can be internal erosion, overtopping, stability, or any other type of failure mode. For the Venn diagram shown here, assuming event A and event B are both potential failure modes, the union of these events is the total probability of failure that can result from these potential failure modes. Breach can occur by failure mode A or by failure mode B, or theoretically by both A and B at the same time. The union equation shown here is for 2 events and is pretty simple, but it gets more complicated when there are more than 2 events. While union is synonymous with or, intersection is synonymous with and. It represents the portion where circles for events A and B intersect and overlap. The probability of intersection is the probability of both A and B occurring at the same time. Evaluation of this probability requires some knowledge about the correlation between events A and B. A good example of intersection would be the events that define a failure mode. If you've completed DLS104, Best Practices in Dam and Levee Safety Risk Analysis, or DLS208, Risk Assessment of Internal Erosion, this diagram should look familiar. It comes from Garner and Venn, and it illustrates how internal erosion initiates when you have the unfavorable coincidence of material susceptibility, stress conditions, and critical hydraulic load. Take concentrated leak erosion, for example. A continuous crack must be present and loaded. There must be an unfiltered exit, the material must have enough fines to keep the crack open, and the hydraulic and shear stress conditions in the crack must be high enough for it to occur. Another example of intersecting events would be for an overtopping failure mode. An overtopping failure would require a flood. The flood will have to be high enough for water to get above the crest, and enough erosion will have to occur to breach the dam. So, the failure probability can be thought of as the intersection of these events. Obviously, the more events you have, the more complicated it gets to account for the intersection. The diagram here shows 4 intersecting events, and I think you can imagine how much more complicated the diagram would become as you add events. 2 events are said to be complementary events when one event occurs if and only if the other does not. For example, a levee breaches or it does not. A dam overtops or it does not. They are complements. You will see this when we discuss the branches of an event tree. In one part of the branch, an event occurs, and in the complementary event tree branch, the event does not occur and is equal to 1 minus the probability of the event occurring. Said another way, when events are complementary, the sum of their probabilities will be equal to 1. Independent events are the events that have no relationship between their probability, and observing one event tells you nothing about the probability of another event occurring. Potential failure modes are typically developed and elicited assuming independence. Assuming independence between potential failure modes, however, is not always guaranteed to be a good assumption. For example, if you have a dam with a gated structure, failure or inoperability of the gates would impact the reservoir stage. As a result, the risk associated with an internal erosion failure mode would be dependent on the operability of the gates because the internal erosion potential failure mode would be dependent on the reservoir stage. Another example where independence would not be a good assumption would be for a dam that has two separate embankments that would overtop at the same time, but where one is much more erodible than the other. If the more erodible embankment breaches first, the overtopping hydrograph of the other embankment changes. So the probability of the less erodible embankment breaching would be dependent on if and when the more erodible embankment were to breach. To calculate the union or intersection between multiple events, we can use De Morgan's rule. We know that the probability of independent events not occurring is equal to the product of their complements. The probability of event A and event B not occurring is equal to the product of 1 minus the probability of A and 1 minus the probability of B. Now that we have the probability of neither event occurring, we can take 1 minus that product to get the probability of either event A or event B occurring. This is the union of events A and B. So the probability that one or both independent events occur is equal to 1 minus the product of their complements. The next slide will give a good illustration of this process. By De Morgan's rule, we calculate the union's complement, the probability of neither event occurring, then subtract that probability from 1 to get the probability of union. Please note that De Morgan's rule assumes that each of the failure modes are independent. Mutually exclusive events are events that cannot occur together. In a Venn diagram, the circles for mutually exclusive events will have no intersection. An example would be a set of Tainer gates, where event A is exactly one gate failing to open, and event B is exactly two gates failing to open. These events cannot both happen at the same time. I discussed mutually exclusive events briefly a few slides earlier and mentioned that it is common to assume flood and earthquake failure modes to be mutually exclusive. In reality, flood and earthquake failure modes are not mutually exclusive as there's some small overlap between them, but the probability associated with that overlap is almost always negligible. If events are said to be collectively exhaustive, this means that the events jointly comprise all possible outcomes. In the diagram, we have sample space S, which is the area inside the rectangle, and we have events A and B. Because events A and B take up the entire area of the sample space, the sum of their probabilities is equal to 1, and the events are collectively exhaustive. When we get into event trees, event tree branches from a node are both mutually exclusive and collectively exhaustive. The final topic in this section is the total probability theorem. The total probability theorem is a fundamental rule that relates marginal probabilities to conditional probabilities. It expresses the total probability of an outcome that can result from several distinct events. The theorem states that for a finite set of mutually exclusive events of a sample space, B1, B2, and so forth, then for any event A of the same sample space, the probability of event A can be calculated by multiplying the conditional probability of A given B by the probability of B at each interval, then summing up the products over all intervals. As will be discussed later in the course, this is what we do when we work through an event tree to calculate the annual probability of failure. The probability of a given load is multiplied by the probability of failure given that load. This is done for all loading conditions, and then those products are summed to get the total probability of failure.